Welcome students. We want to discuss about chain rule today. So I'll start with this quote by Michael Atiyah. Atiyah was a famous algebraic geometer. He's a mathematician. Um, he was a Fields medalist as well. In the broad light of day, mathematicians check the equations and their proofs, leaving no stone unturned in their search for the rigor. But at the night, under the full moon, they dream, they float among the stars and wonder at the miracles of heaven. They are inspired. Without dream, there's no art, no mathematics, no life. Okay, very powerful quote. So in this lecture, we want to generalize the chain rule from function of one variable to function of two variables or function of many variables. So let's start. Recall, how did the chain rule for one-dimensional calculus look like? So suppose your is a function of f is a function of x and x is a function of t. Then you have chain rule tells you derivative when you want to take f of x of t, then it is derivative of outer function evaluated at inner function multiplied by derivative of inner function. So this is what the chain rule is for function of one variable. Now suppose we have function of two or more variables. Let's look at this example first. So falling stone forms a conical sand pile. So you have a conical sand pile forming out of the falling sand. Now, when the height is 5 meters, so when the height is 5 meters, and when the radius is 2, so when the radius is 2, the height is increasing at the rate of 0.4 meter per minute. So suppose you have h is height, r is the radius, and you're given that your volume V equals to, well, the formula for cone is 1 by 3 pi r square h. And you are interested when at this time, when the height is 5, radius is 2, h is increasing at the rate of point dh by dt is 0.4 minute per minute, meter per minute, dr by dt is 0.7 meter per minute. What is dv by dt? So if you look at this problem carefully enough, you are having volume, which is a function of two variables, r and h. And r and h in themselves are function of one variable, which is t. So how do we find out dv by dt in this case? So that is what we're going to do now. So let's start with the following version of chain rule. So suppose z is a function of x and y. It has continuous first order partial derivative, and x equals to g of t and y equals to h of t are differentiable functions. Then z is also a differentiable function of t, and if you want to compute dz by dt, dz by dt is partial derivative of z with respect to x times dx by dt, partial derivative of z with respect to y times dy by dt. So this is a chain rule for function of two variables. So let me draw a tree diagram that is really helpful to understand how things go here. So you have x, this is a function of x, this is a function of y, and each of them is a function of t. So your x is a function of t, your y is a function of t. So then dz by dt, right? So z totally depends on change in t. That's why it is written d by dt, not partial derivative of z with respect to t, right? It's a complete derivative, right? So the way we compute it is as follows. So we go along this path first. So we'll get what? We go along this path and this path. So we get this is equal to, now z is not just function of x, it's also function of y. So when I'm writing that, I'm going partial derivative of z with respect to x. Now this one here would be dx by dt because x is completely function of t. Similarly, now you have to approach along the other branch. So you go like that. So we go like this and that. And now the other way around. So we'll go along this branch now. So partial derivative of z with respect to y times dy by dt. Again, when it is only y is only function of t, then you'll use d. If it is partial, if it's function of not just, so in this case again, z is not just function of y, so I'll use partial derivative of z with respect to y. Okay. So this is the chain rule. So first version of chain rule. So there are many versions depending on how this y is a function of t or more variables. So we'll see those as the time comes along. So let's look at the following problem. So we have z equals to arctan of x squared plus y squared with x equals to t squared, y equals to t cubed. So again, I'll write, the tree helps me out. So I have function of y and these are function of t. So let me write down dz by dt is partial derivative of z with respect to x times dx by dt. So I went along this path here to all the way to t plus I have, then we have what we have. Now we have to go along this guy, this path. So we get what? D partial derivative of z with respect to y times dy by dt. So now let's compute these objects. So what is partial derivative of this with respect to x? So arctan derivative is 1 upon 1 plus multiplied by, now here I'll use the chain rule for the partial derivative, again times x squared plus y squared, which is going to be 2x upon 1 plus x squared plus y squared, the whole square. Similarly, I get with respect to y is going to be same thing, symmetric. The equation is very symmetric. So x squared plus y squared. And we get dx by dt. So we are getting all the integrants set to t, and dy by dt equals to 3t squared. So therefore, we get dz by dt equals to 2x 1 plus x squared plus y squared the whole square times 2t plus 2y 1 plus x squared plus y squared the whole square times 3t squared. Okay, you can leave it at that. You don't have to substitute x equals to t unless x equals to t squared or y equals to t cubed unless specifically asked. Now the same thing can be done here as well. So here we have, this is a three-dimensional generalization of this. So your w is a function of x, y, and z. And this is a function of t. This is a function of t. This is also a function of t. So let me write down the, so now, and at the end of the day, w is just a function of t where x, y, and z. So then I can write down the total derivative equals to partial derivative of this with respect to x times dx by dt, partial derivative of w with respect to y times dy by dt, partial derivative of w with respect to z times dz by dt. Now let's compute what is partial derivative of w with respect to x? Again, by the previous formula, we'll get 1 plus x square plus y square plus z square, the whole square, times partial derivative of w with partial derivative of x square plus y square plus z square with respect to x, which is going to be 2x. Similarly, we can find out 2y is 2y upon 1 plus x square plus y square plus z square, the whole square, and the z is going to be 2z upon 1 plus x square plus y square plus z square, the whole square. And now I need dx dy dt. So dx by dt is dx by dt equals to 2t, dy by dt equals to 3t square, dz by dt equals to 4t cubed. Now we just need to substitute there. So this implies dw by dt equals to 2x 1 plus x square plus y square plus z square, the whole square, times dx by dt, which is 2t, plus 3t square times 2y upon 1 plus x square plus y square plus z square, the whole square, plus 2z upon 1 plus x square plus y square plus z square, the whole square, times dz by dt, which is 4t cube. So this is the complete derivative. So now coming back to our original problem, so we have v was 1 by 3 pi r square h. So your v is a function of r and t, sorry, r and h, and they in turn are function of t. Yeah, so let's compute this. So what is dv by dt going to be? Dv by dt is partial derivative of v with respect to r times dr by dt, because r is completely a function of t, plus partial derivative of v with respect to h times dh by dd. Now, what is partial derivative of v with respect to r is 1 by 3. So we get 2 by 3 pi r h times dr by dt. And here we'll get dv by dh is 1 by 3 pi r square times dh by dt. So therefore dv by dt is, let's organize this a bit. So 2 by 3 times pi times r. What was our r? R was at that moment, r was 2, so times 2. H at that moment was 5. Dr by dt at that moment was, dr by dt was 0.7. These are multiplied, plus 1 by 3 pi r square, which is going to be 2 square times dh by dt, which is 0.4. So if you simplify, this is what we'll get, meter cube per minute. So connect with the product rule here. connect this with product rule of function of one variable and see if they both match. Function of one variable. Okay, and then you can see that both of them will match as well. So this is the setup. Now suppose you have several independent variables. So the idea is you have W, which is function of X, Y, and Z. So your W is, so we have W is function of X, Y, and Z, and they themselves are function of U and V. Function of U and V. Function of U and V. Okay, so yeah, so I can write this as, it's better if I write it as X of U V, Y of, it's clear that X is also function of UV if I write it like this, Y of UV and Z of UV. Yeah, so this should, I should replace this by X and Y so that it fits well with the setup. So now the question is, I want to compute. So now what can we compute here? We can't write dW by du anymore, right? Because u is not just function of, if you walk down this path here, if you walk down this branch here, you will see that u is not just function of, sorry, w is not just function of u anymore. It's also function of v. So we can't write down dw by du. We have to use the partial derivative. So it's going to be partial derivative of w with respect to u. So now what you have to do is, to remember the formula, you have to go from w all the way to u along different possible paths. So what are the different possible paths? So one path is here to go from w to u. So it will be all partial in this case. So this is going to be partial derivative. So now let's go along this path. So partial derivative of w with respect to x, and then multiplied by partial derivative of x with respect to u. That was one path. Secondly, let's go along this one here. Go to, so in this case, we get partial derivative of w with respect to y times partial derivative of y with respect to u. Similarly, let's go along the next one now. Now, what is the other remaining path we can take to go to u? Is this one here. So we get partial derivative of w with respect to z times dz by du. So this is the partial derivative of w with respect to u. Now we can basically write down the whole thing again. Let's write it down. So we get, with respect to v, it will be the same thing except for the fact that we will be choosing path going to u. So from here, then we'll go this way. Yeah. So for all of them. So let me write down the formula quickly. So we have by x times, now what is getting replaced is the first part is same, this part here. Instead of dx by du, you have dx by dv. Similarly, the first part remains the same. You have dy by dou y, sorry, I shouldn't say d, dou. So I'm going to use dou for partial derivative. Yeah, I mean, it's shorter than calling it partial derivative all the time. So all the derivatives involved here are partial derivative, right? So dou y by dou v plus dou w by dou z times dou z by dou v. So this is the the chain rule for function of three variables where each of the variables themselves are function of two variables. Okay, so let's look at the following problem. So we need dou w by dou u. Again, it's always a good idea to have a small tree on the side. So your w is a function of x and y, and your x and y are function of u and v, u and v. So I'm going to write down the formula. So again, with respect to x, so I'm going along this path now. So I have dou w by dou x times dou x by dou u. Now I'm going along this path, which is so I'm going to go dou w by dou y times dou x by dou y times dou y by dou u. So let's compute this. So we have what is dou w by dou y. I'm going to do this on the fly. So derivative of cos is sine, sorry, sine is cosine. So cosine x squared y multiplied by derivative of inside with respect to what? With respect to x, which is going to be y is a constant comes out, derivative of x is x squared is 2x. So this part is just here. Now what about the other part? Multiplied by, so multiplied by dou x by dou u. So let's see. So this is going to be just simply 2u. So I'm going to mark it so that you see the correspondence. Plus, now dou w by dou y. So again, derivative of sine is cosine. So cosine x squared y multiplied by derivative of inside x squared y with respect to y. That's going to be x squared times dou y by dou u, which is going to be again 2u. So if you, this part became this and this part became that. So this is your partial derivative with respect to u. Now I want to write down the partial derivative with respect to v. So you should be able to reuse some part of your previous computation. So for example, in the formula, if you look carefully, we have this part is going to be the same. The only new thing is here we have dou x by dou v. Similarly, the first part remains same for this guy. We have dou y by dou v as well. Okay, so we can reuse what we, so we can reuse these parts from the previous one. So let's write that down. So we have dou w by dou x is going to be again cos of x squared y times y times 2x. Now dou x by dou v is 2v. Similarly, dou w by dou y is cos of x squared y times x squared, and dou y by dou v is minus 2v. So this is the setup. All right. So this is how you deal with, again, and this can be generalized to function of many variables. All right, straightforwardly generalized. Okay, so all you have to do is the tree diagram comes very handy. So let's move on to this problem now. So this problem is slightly interesting. Here you have, suppose w is a function of u, v, x, and y. Okay, so it's a function, seems like function of 4 variables, where u and v themselves are function of x and y. So there's a small twist here that we have, if I want to write it, w as f of u is a function of xy, v is a function of xy, x is a function of x, well, and y are the independent variables. So these two are independent variables, and x and y are independent variables. So independent variables. Now the question is, how do we find out dou w by dou x and dou w by dou y? Again, the same thing. You need to basically be able to write down the tree diagram. So we have u, w is a function of u, w is a function of v, but w is also a function of what? X and w is a function of y. These guys on their own are function of x and y. This is also a function of x and y. This is the function of x. And this is not a function of x, right? So this is function of only y. So let's have this kind of a tree structure. So that will help us to compute it. So again, so let's compute partial derivative of w with respect to x. So now we have to go from w all the way to x. So let's see what is the first branch. The one branch is, take this branch down. So then the second would be, I will take this branch down. Then I will take this branch down, and well, this is the only ways to go to down to the thing. So we have dou w by dou x is dou w by dou u times dou u by dou x plus dou w by dou v times dou v by dou x plus dou w by dou x times dou x by what? Dou x by dou x by, so now x is just a function of x. So I'm going to write dx by dx, which is 1, right? So this is 1. So I'm going to ignore that. So this is my dou w by dou x. So it's more customary to write, actually it's customary to write this as function of f. So if we write it better this way, sorry, so we should write this as function of f, because so this will be dou f by this, dou f by this, and then dou f by dou x. Similarly, we have dou w by dou y equals to dou f by dou u times dou u by dou y plus dou f by dou v times dou v by dou y plus f by, yeah, it would be wrong to write dw by dy here, all right, yeah. So you're taking f and differentiating that with respect to y as a function. Okay. So this is the setup. Now we want to talk about the implicit partial differential equation. So suppose you have function f of x, y, z is a continuous first order partial derivatives, and the equation f of x, y, z equals to 0 implicitly defines z equals to f of x, y. That has continuous first order derivatives. So the derivatives are nice. Then dou z by dou x and dou z by dou y are given by the following formulas. So let's approach this problem. So now you may say, well, if I write it like this, then I have function of 3 independent variables, and that is correct. So, but however, when you equate it to 0, you are making a dependency among the variables, and hence we get basically that we get essentially that it becomes a function of 2 variables, namely z becomes implicitly the function of x and y. So again, so let's look at the following. So we have here f of x, y, z equals to 0, right? So we have, again, let's take so suppose I have this f of x, y, z equals to 0. So differentiate both sides with respect to x. So we have, if we differentiate on both sides, we get partial derivative of this f of x, y. Now your z is implicitly, it's a function of x, y, even though implicitly equals to 0. Yeah, partial derivative of 0 is 0. So now let's apply the rule here. So we get partial derivative of f with respect to x plus partial derivative of f with respect to z times dou z by dou x, because x is a function of 0. Right? So again, the idea is you have f, z is a function of, z is a function of x and y, x, y, and z, and your z itself is a function of x and y. Okay. So from here we get, what are we looking for? We are looking at partial derivative of z with respect to x. This is going to be minus partial derivative of f with respect to x divided by partial derivative of f with respect to z. Yeah. And similarly, if you differentiate both sides with respect to y, so let's call this a star, differentiating star with respect to y, this will give us again partial derivative of f with respect to y plus partial derivative of f with respect to z times dou z by dou y equals to 0. So this gives me dou z by dou y equals to, again, minus dou f by dou y divided by dou f by dou z. So this is an implicit partial differential equation. Now we'll see how it is useful for us. So here, so in this case, you're given, let's look at this example now. So z be a function of x, y, such that z cube minus z plus 2xy equals to this, and we have z of 2, 4 is this 1, and we want to find out linear approximation. So first of all, what is the formula for linear approximation? So z of xy is z of 2, 4 plus partial derivative of z with respect to x evaluated at 2, 4 times x minus 2 plus partial derivative of z with respect to y at 2, 4 times y minus 4. And this is a linear approximation. So since it's an approximation, I'm going to use the same approximation. So now let's see. So this is already given to you as 1. Now we need to compute these guys. Yeah. So we have to use the formula, which is over here, right? So we have to use this formula here, right? So let's use that formula. So we have, again, so either use the formula or you can do it implicitly. So I'm gonna do without using the formula. So let's just do that. So differentiate both sides with respect to, take this equation and differentiate star with respect to x. So differentiate star with respect to x. So what do I get? I get 3z square times dz by dx minus dz by dx plus 2 Now I'm differentiating with respect to x, so 2 will become 2y minus 0, so equals to, I'll get derivative of that is 0. So we get here equals to plus 2 equals to, and then I get on this side, I get 0. So therefore we get, bring everything on the other side. So we have dz by dx taken common, and I'm moving everything on the other side. So this goes on the other side, becomes minus 2y. And then I'm dividing it by 3z squared minus 1. So therefore, this implies dz by dx at 2, 4 is going to be minus 8 divided by 3 times z square. So now z at this point is 1. So 3 minus 1, which is going to be minus 4. So now the other one is we'll differentiate star with respect to y. So differentiate star with respect to y. So again, we'll differentiate this with respect to y. So we get 3z square partial derivative of z. So dou z by dou y minus dou z by dou y. Now derivative of that is simply 2x. Derivative of minus y square is minus 2y equals to 0. So this gives us partial derivative of z, x with respect to y is going to be 2y minus 2x, just bringing this on the other side, divided by 3z squared minus 1. So this implies partial derivative of z with respect to y, 2, 4, is going to be, again, the denominator is 3 minus 1, so that is 2. On numerator, we have 2 times y minus x. So 2 times y minus x. So sorry, that did ink to the corrections. Let's write it down. Here, 2 in the denominator, and I have 2 times y minus x. So y is 4. 4 minus 2 is 2. So 2. So the answer is 2. So therefore, our equation becomes, we get this is equal to 2, right? So now we can get the equation now. So I'll write down the equation here. So therefore, linear approximation is z of xy equals to, so again, continuing a here because there's a shortage of space. This guy is equal to 1 plus partial derivative of z with respect to x at 2, 4 is minus 4. So minus 4 times x minus 2 plus partial derivative of z with respect to y, this thing here is 2. So 2 times, so we get 2 times x minus 4, sorry, y minus 4, my bad, right? It's y minus 4. Y minus 4. So this is your linear approximation function. So now we can compute, let's compute the part B, which is the estimation. So z of 2 point, so this is again approximation. So z of 2.2 comma 3.96 is just simple substitution. You have, instead of x, we are going to substitute 2.02 plus 2 times 3.96 minus 4. And if you want to simplify this, this is going to be 1 minus 2. Okay, so x minus 2, right? So x minus 2 is y minus 4. So, okay, so minus 4 times 0 0.2, actually 0 0.02, right? So 0 0.02 plus 2 times 0 0.04 with a negative sign. So that is going to be minus 0 0.08 minus 0 0.08. So this is going to be minus 1 minus 0 0.16, which is going to be 0 0.84. So this is the linear approximation of your function. Right. Now let's look at the following problem. So we have x is a function of uv, y is a function of uv, and u and v are implicitly defined function of x and y near points x equals to 2, 0, and uv is 1, 1. Compute dou f by dou y at point xy equals to 2, 0, and z equals to u square, v square, compute this point. Okay, so let's embark on this now. So problem 11 is also about implicit differentiation. So you have here that u and v are implicitly defined as a function of x and y. So u is a function of x, v is also, u is a function of x and y, v is a function of x and y. And then you have to basically find out what is dou u by dou y and work this whole thing out. So I will leave this problem as a homework, and if not, we will discuss it later. Okay, thank you for your attention.